Okay, so now let's talk about second part in section 11.6. Yeah, it's about tangent plane and the normal line. And our goal is to find the tangent plane and the normal line as for this function. It's for this function at some point it's tangent line and it's normal line. I mean for x, y, z, if it satisfies this equation, and here I just give you the example. For the XYZ point, it's in three-dimensional coordinate system. If XYZ satisfies this equation, it has a graph, and in this graph, I want to know at some point it's tangent plane. Yeah, for example, I want to know 1, 1, 0. This point is in satisfy this equation, so it's in the graph, its graph, and we want to know its tangent plane. And the normal line. And for this question, we have a general formula, and I will tell you the formula. But for the idea to get this formula, it's complicated because we have three variables. But when we consider this question, we should think about view as a label surface of a function which contains three variables. So it becomes complicated. So now I will explain it by the simple case. I mean by the case. For this case, we have the general formula. If the function has in this equation we have three variables, but if the equation contains two variables, we also have similar formula. So it could be as just a special case for this case. So for its formula, I will explain the case when we just have two variables. And for three variables, then just consider the similar case. Just use similar formula. Yeah. So I just explain this one, and to tell you the formula in this case. And in this kind of case, then we have similar form for its formula. Okay. Anyway, so let's see this example. So we start from this example. Yeah. Okay. So here I will see. Okay. So what I want to say is that originally for this example, we want to find in this point 1, 1. It's in this point 1, 1. 1, 1 is satisfied this equation. And x squared plus y squared equals 2 is probably, it's exactly this circle, and here is square root of 2, 0, 0, square root of 2. And we want to know this point is tangent line, and it's normal line. It's tangent line and it's normal line. Yeah. And of course we know we have the formula. We could do it by the result in chapter 1 or chapter 2. Yeah. But here I just want to explain it by another way. Because for general form, I will also solve it. Yeah. In this way. Okay. So, and how about this? So here, for this function, actually I view it this way. I define a function g. I define a function f of xy by this one. I define a function f of xy. Define it by x squared plus y squared. I define a function f of xy is defined by x squared plus y squared. Then what does it mean? It means that now we consider g. We denote it by g. G equals f of xy equals x squared plus y squared. So for this function, for xy equals 0, it's just 1 point. For this function, if g equals 0, s equals y equals 0, right? And then when g equals 1, it satisfies x squared plus y squared equals 1. When g equals 2, it satisfies x squared plus y squared equals 2. What does it mean? Actually, it means the label curve, right? Do you remember that? it's our label curve. When g equals 1, it means the height is 1. It's high. In its graph, if its height is 1, then we can say it's projection. Then we can get this one. And here it should be this one. Here it should be this one. It's a circle. This one. And when the height is 2, when the g value equals 2, we have, once we fix the constant 2, and for the function, if fxy equals 2, we have a circle. In this example, it's a circle, and we can see its projection, and it is this one. And here is this one. Yeah. Here is this one. It's a circle. This one. It's a circle. Yeah. Okay. Yeah. So now we want to know, as we say, gradient f110. Actually, how to, yeah. And okay, so for this one, if you want to know its tangent line, how to solve it? In chapter, let me see. Okay, so if satisfy this equation, x squared plus y squared equals 2. So now f of sy, we define f of sy by this way, x squared plus y squared. So what can we say? F of sy equals 2, right? What can we say? This one. But if xy satisfy this one, then y is related to x. So you could view y as a function of x. I should use another notation. Here it's the material. It's related to the material in chapter 11.5. It's an application of chain rule. But for this part, probably I skip some part. Yeah. So here I also explain some in. Yeah. Anyway, we could just use the chain rule directly. Use chain rule to explain it directly. Anyway, so here we have the function. So you could view it this way: 2 equals f of x. And then here we have two functions. Y is g of x. This one. And recall chain rule. For the chain rule, we have a result. If g equals f of x, let me see, h of x, g of x. And x equals, let me see, which notation I use. H of x, g of x here. Okay. Originally I say, okay, let's find, okay, x equals g of st, and s equals g of x, h of x, t equals g of x. And what's the, we could consider dg dt, right? Because s is this one, dg dx. St is this one. Yeah, so dg dt is this one. F for the function f, it has two variables. So we can say f sub s, f sub t. And here we could consider ds dx plus dg dt dx. This one. Okay, this one, right? And then now for this one, we want to use the chain rule. So we want to use the chain rule. But in this chain rule, you could see that S here, what's this? What's this? It's exactly here y equals g of x. So here h is exactly x equals h is exactly equals this one. So here here we replace s by x, right? By x. And the t is our y, t is g of x, and g of x is our y. Here is our y. In this case, is our y, dy ds, and dy ds. This one. So, what does it mean? What does it mean? I mean, for its, we have two terms, f sub x, f sub y, and this term is d dx ds plus dy dx, this one. And the left hand side is constant. Sy satisfies the equation, so it's constant. So its derivative is 0. Its derivative is 0. This one. So it satisfies this equation. And in this equation, you could see that d dx ds is 1. So what do you have? You have this one. dy ds equals 0 equals f sub x plus f sub y times dy ds. So dy ds equals, move e into left hand side, so it's negative f sub x divided by f sub y. We have this form. We have this one. dy ds is this one. Okay, and here for this part I just explained by chain rule. But for this part, if you just check this example, you will get better, because here we have this one, and if you remember that, as we say, just view y as a function f of x, g of x, right? As we say, g of x. So what do we have? G of x is square. So consider its derivative. So left hand side is 0, right hand side is 2x times 2x, just 2x, right? So you could view it this way. Here is ds ds. ds ds is 1. I just want to say this equation is exactly this one. Plus 2g of x times g of x is 2g of x times g of x is derivative. This one. And here 2x is our function f of sy is this one. So you could see that what's f sub x? F sub x is 2x. F sub y is 2y. F sub y is 2y. This one. So here 2x is exactly our f sub x. And 2 of y is exactly, if you put it back, it's 2y times dy ds. It's 2y times ds. So this part of 2y is exactly f sub y. And dy ds is what we want. Yeah. So here is actually we just used the implicit differentiation before this one. Yeah, but we also could explain implicit differentiation by chain rule. Okay, so what do we have? You will get dy ds is exactly equal to, move it to left hand side, so it's negative 2x and divided by 2y. Negative 2x divided by 2y. And it's exactly this one, right? Our f sub s is 2x. The f sub y is 2y. So it's exactly this form. So in other words, for its tangent line, its slope, dy ds is the slope of tangent line. The slope of tangent line is exactly this one. Negative f sub s over f sub y. Negative f sub s over f sub y. And this one it holds for general case. Even it's not f of sy is not of the form s squared plus y squared. We also have the same result. And how to get it? Just use the originally what we showed in chain rule, by chain rule. Okay, so we have this form. Okay, so now I erase this part and write down this one. But I just keep this one. dy ds equals this 10. So let's see what's the tangent line. And okay, so it's general case. What do I mean? Here, in this example, we just consider the case. For example, we consider this one, and we denote by f of sy, right? So general case is if sy satisfies this equation, f of sy equals some constant k. Okay, so it's general case, and the graph is similar. The graph is similar. Okay, so we can say g equals f of sy, and this point is our s0, y0, and now we want to explain. I want to explain that gradient vector means this one. Gradient vector means the one. Okay, I remind you, what does gradient vector mean? It means that if we consider the point s0, y0, and of course g plane is in xy plane, so g value equals 0, and it has a corresponding value once we apply in the function f of sy. So it has a height f of s0, y0. If we denote by k, now we fix the constant k, and so in the graph it must have a curve. And in each point in its curve, but all of them have the height k. All of them have the same height k. It means that their g value equals k. And we can see its projection, and probably its projection is this curve. And so in this curve, the variable sy satisfies this one. So what does gradient vector mean? It means that for this curve, of course, you will pass through this point s0, y0, 0. So you could consider a tangent line, and you could consider tangent line. You also could consider second line, normal line. So gradient vector means the normal line. I mean, gradient vector is the direction in normal line. It's the direction vector in normal line. Okay, and I would like to explain it here. Okay, so how to say that? Now our original, if we want to know graph a line, and we know that it passed through the point, and it has a slope. We know its slope. Then how to get this line? We have the form, right? Y subtract y0 equals slope. Divided means the slope, right? It's slope. So y subtract y0 equals m times x subtract s0, right? We could use this formula, right? Okay, so we use this formula. Y subtract y0 equals the slope of the line. The slope of the line is this one, right? Originally it's dy ds, but as we say in previous result, it's exactly this one. Negative f sub x s0 y0. Sorry, yeah. dy ds, but you should plug in the value s0 y0. So dy ds, so it's negative f sub x s0 y0 over f sub y s0 y0 s sub s0. So the tangent line is this one. F satisfies this equation. Let me remind you. So again, we could get a gradient. I mean, we could get f sub s, f sub y. We could get this one. Okay, so let me see. Oh, what I mean is we denote we let g consider g equals f of sy, so I should say that in this way. Yeah, we did not just follow this one. G equals f of sy, so of course we could consider s sub a f sub y. Okay, so now but for this one, we multiply by the 10 in denominator. Then what can we have? F sub y s0 y0 times y sub 2 y0 equals negative f, this one. And then move it to the left hand side, then general form is this one. Finally we get this one, fx s0 y0 s subtract s0 plus fy s0 y0 fy subtract y0. The tangent line pass through the point P is this one. This one. And I explain it later. And okay, so now how about normal line? If you remember that for this normal line, you also pass through this one. S0, Y0. But how to get, what does normal line mean? If here is S0, Y0, if we know the tangent line, normal line means that they are orthogonal, right? They are orthogonal. And here we have a slope n. And for the normal line, we also have a slope n sub 1. And the slope n is equal to dy dx. And it's equal to negative, dy dx is negative fy fx, this one. Dy dx is this one. This 10. And what's the relationship? The relationship is n times n sub 1 is equal to negative 1, right? Since they are orthogonal. Okay, so what's the slope of n sub 1? The slope n sub 1 is negative 1 over n. So it's reciprocal. So its reciprocal becomes f sub y over s sub x. And here we have negative, and we also have a negative, so it becomes positive. So it's exactly this one. The slope of normal line is this one. And it passed through this point, so we could write down again y subtract y0. Here the slope is this one, f sub y s0 y0 s sub x s0 y0 times s subtract x0. Later I will give you the general result and give you examples. Yeah, for examples, actually if you just follow the formula, it's not a difficult one. But how to get this one, I should explain some. Yeah. And for this 10, we could rewrite it by this way. Here, for the numerator, we put in the left hand side. I mean, we divide by this 10 f sub y in both sides. So what can we have? We have this 10 x sub left hand side. We still have this one, right? Left hand side we still have this 10. Right hand side we just move the left hand side. So it means that we divide this 10. So it's equal to y subtract y0 f sub y is 0 y0. This one. So the normal line at this point is exactly this one. So what can we say for this vector f sub x, s0 y0 f sub y? What can we say for this vector? For the gradient, what can we say for the gradient vector? It's f sub x s0 y0 f sub y s0 y0. What could we say for this gradient vector? Here I erase all of them. Okay, so what could we say for this gradient vector? You could see that it's exactly the coefficient of x, coefficient of y, right? Coefficient in the denominator, right? So what can we say? If you remember the result in chapter 10.5, when we say a plane, we have a plane. In three-dimensional case, we have a plane S. And for the plane S, it has the general form ax plus by plus cg equals plus d equals 0. Then what's the coefficient mean? What's the coefficient mean? Coefficient means that it's normal vector, right? It's normal vector. It's a normal vector, right? And how about two-dimensional case? It's the same, right? I mean, it's the same. If we have a line, and for the line, we could use the same way, same argument. We could use the same argument. We could consider, if I give you a normal vector, I mean, a vector which is orthogonal to this line. So, and we also call it AB. And for this point, I also denote it by S0, Y0. And for any point SY, what do we have? We have this one. And these two vectors, they are orthogonal. So we know that here, if I denote it by A, B, then we know that the normal vector N is, and the AB, they are orthogonal, means that their inner product equals 0. So AB S subtract S0, Y subtract Y0 equals 0. So AX subtract S0 plus B, Y subtract Y0 equals 0. Right? So distribution, you will get AX plus BY subtract AX0 subtract BY0 equals 0. So you could see that what's the coefficient mean? AB means the normal vector. I mean the vector is orthogonal to the straight line. So when you see the coefficient, what does it mean? It means that it's orthogonal to this tangent line, this line. So gradient f of sy is exactly this vector, right? It's orthogonal to this line, tangent line, this line. This line means the tangent line, right? Here, it's the tangent line S. It's the tangent line. So gradient means that it's a you could view it as a normal vector to the tangent line. And even in this case, it's the same. You also could explain it by this way. I mean, in three-dimensional case, in chapter 10.5, we also say that we have the form. If I give you a straight line, a point S0, Y0, Z0, and I give you a vector ABC. And for this line, we have the direction. For any vector in the line, it's parallel to this vector. Then what do we have? We have this result. A, B, C. Right? We have the symmetry equation. In its symmetry equation, in the denominator is the vector, which is parallel to any vector in the line, ABC. Right? So now, even in two-dimensional case, it's the same. It's similar. Use similar argument. We have the same result. I mean, we have this form. It's the same. And you will see, indeed, what do we have? What could we say about the denominator number? It's exactly the vector in the line, right? So it's exactly the vector in the normal line. Gradient is exactly the vector in normal line. Okay. Yeah, so I just explained it by the case f of sy equals k. But now we want to say for our original question is this one: x squared plus y squared plus z squared equals 2. So we should consider this case: fxyg equals k. We have three variables, right? So in three variable case, we also have similar argument. I mean this form. In this form, we have two variables, so it's f sub x, f sub y. So if we have three variables, it becomes f sub x, f sub y, f sub g. And here it's the same. Three variables, it becomes f sub s over f sub s, f sub y, f sub g. Okay. and I write down the formula. I write down the formula and give you the examples. Yeah. Okay. Just due to time, I have not introduced too much information. For example, in implicit differentiation, I have not introduced too much. Yeah. So, but we will use them. So I just tell you, and probably, and I also have given you the examples, right? Yeah, x squared plus y squared equals 2. You could use this example to think about it, to think about a general case. Okay, now I write down the form. The result. I write down our result. But before that, we will use the notation, the definition. The tangent plane. To the labels surface fxyg equals k. As we say, if we say f of xy equals some constant k, then it's a label curve. But now if we have 3 variables, then the name is called label surface. Label surface. It's defined by the plane that pass through P and has normal vector. It's gradient. So what does the tangent plane mean for the label surface? What does at some point, what does the tangent plane mean? It means that it's the plane that passes through the point P and has the normal vector gradient. So gradient, if the gradient is normal vector, then we define it's exactly the tangent plane. The tangent plane. Okay, it's a definition. And of course, the gradient is non-zero. Gradient is non-zero. Now let me write down our result. First one, and I give you the example. The tangent plane to the label surface. Normal line to S P E. Here is its gradient. S0 y0 g0. Its gradient. S0 y0 g0. Its gradient. S0 y0 g0. And it's the same, the gradient is 0, y0, g0. It's a gradient, it's 0, y0, g0. It's a gradient, it's 0, 0, y0, g0 in denominator. And the numerator is s sub s 0, symmetry equation. symmetric equation. So that's why we say for this result, it's complicated to it's abstract to explain it. It's abstract. Yeah. So we just explain two-dimensional case. And in particular, actually, if you remember that, actually, we skip section 111.4, and the reason is that one of the reasons is we don't have too much time, and the second reason is that actually for the result in section 11.4, it's just a special case for this result. It's just a special case for first result, and I explain it later. In particular, if the stable surface S is this one, G equals f of sy. I will give you the example. Then the tangent, if S is this one, the tangent plane to S at P S0 Y0 is, let me see, G subtract 0 equals fx s0 y0 s subtract 0 plus fy s0 y0 y subtract y0. It's this result. And here I explain this result. Yeah, first one, second one is similar as the previous case. Yeah, but it's our general result. Yeah, here is, if it's tangent plane, we can see for its gradient vector, we put the coefficient. And for a normal line, just put it in the denominator. It's a symmetric form. And it's also the reason why we introduce chapter 10.5. And actually we use it here. And for the third result, here the surface is this one. And it means that in this case, what does it mean? It means that XYZ satisfy this equation means, give you an example. For example, it satisfies this one, right? And in this case, G is not a function. It's not a function of xy, right? Because here is G squared, so it's not a function of xy. In general, G probably is not a function of xy. But now, if it's a form, then G is a function of xy. For example, G equals x squared plus y squared. In this case, G is a function of xy. In this case, G is a function. So, if we G, in particular, if G is a function of xy, then we have this form. And it's exactly the material in section 11.4. Okay, so how to get this one? As we say, it's a special case in this one. So now, let's see what's the relationship. If you want to use this result to solve this one, then you could see, you should have the capital F function, right? So what's the capital F function? You should consider their relationship. So now actually, if we combine them, I mean, just move it to left hand side. So divide it by this way. G subtract f of xy. Then for any xyg, if we satisfy this equation, if it's in the surface S, if it's on the surface S, then capital F of syg will be equal to 0. It's equal to 0. So it will satisfy this one. So we could use this result. And so in this result, you should consider f sub x, f sub y, f sub g. I mean it's gradient. So you should know it's gradient. So what's the capital Fx, capital Fy, capital Fg? Capital F function is this one, capital F of s. And in this case, all of them are independent. So capital F, so if the variable s, we could view y and g as constant. So here is 0, it's negative fx, this one. And capital Fy is 0, its derivative is 0, subtract fy. And here it becomes 1. And they are constant. If our variable is at g, so it's 1. So what do we have? Here the first part is negative fx. X subtract s 0, subtract fy, y subtract y 0, plus 1 times g subtract g 0 equals 0. This one. And then now, just move these two terms into right hand side. Then you will get this one. Right? Yeah. So it's just the special case. Okay. Yeah, so now I give you the example. Yeah. Now I will give you the example. Actually, if you just memorize this result, and when you apply for this our formula, it's very quick to solve it. So we spend lots of time in explaining the formula. I mean, probably give you the idea about the formula. Okay, so now I give you the example to solve it. So here we have the example. Find equations of tangent plane and the normal line. The first one is -2. First one at the point -2, 1, -3 to the digit. So x squared over 4 plus y squared plus g squared plus y squared plus g squared over 9 equals 3. Second one at the point 0, 1, 0 to the surface. X plus y plus g equals exponential x, y, g. This one. Okay, so it's our last question in this chapter. And then of course we just consider our formula. So in our formula, as we say, first of all, you should consider its gradient. Their gradient, but you should define a capital function f. And for the point in its capital function, it satisfies this one. So I mean, we should define a capital function f. So for the first question, we define capital F as capital F. And here, of course, we define it by this way. I mean, square over 4 plus y square plus g square over 9. Of course, you could subtract 3, or you could just keep this one. That's fine. Because if x, y, g satisfy this equation, it means that it's on the surface S. So when you plug in the capital function f, you will get f of s, y, g equals 3. But if originally you define the function f by the way this 10 subtract 3, then it will be equal to 0. So that's fine, that's fine. Just define it by this way or subtract 3, that's fine. Anyway, you have this form, so we could apply for our formula, and then apply for our formula we should consider its gradient. So its gradient is, what's this? Fx, y, g, right? So what's this? If we consider the derivative with respect to x, then we should view y and g as constant. So it becomes, this guy, its derivative is 2x over 4, right? And then second 10, then we just need to consider second 10 its derivative. So it's 2y. And again, just need to consider third 10 its derivative, 2g over 9. The reason is that the previous two 10s are 0. Previous two 10s are 0 when we consider this one. Okay, so you get this one. And we consider this point, so you should consider at this point, negative 2, 1, negative 3. So it's exactly, here it's exactly negative 2 times negative 2 is negative 4 over 4, 2 times negative 3, negative 6 over 9. So it's negative 1, 2, negative 2 over 3. This one. So once we have this one, we could write down the solution directly, right? Tangent 9. The first question is tangent 9. Second question is normal 9. Actually, we could write down the solution directly. Just follow just follow our formula. Our formula is that the gradient vector for the tangent 9, put it in for the tangent 9, it's just the coefficient of our x, y, z, right? So it's negative 1 times plus 2 times subtract 2 over 3 equals 0. But inside we should consider s subtract x0, inside is s subtract x0, y subtract y0, g subtract g0, this one. So it's x subtract negative 2, so it's x plus 2. And the y subtract y0, so it's y subtract 1. G subtract g0, so it's g subtract negative 3, so it's g plus 3. This one. So the tangent line is this guy. This guy. And the normal line becomes this one. It's negative 1, 2, negative 2 over 3 in denominator. Negative 2 over 3 in denominator. This one. And the numerator is this 10. S plus 2, y subtract 1, g plus 3. Right? Just the solution. Use the formula. You could write down a solution directly. This one. And yeah, and so now let's see the second question. And it's similar. So we still construct a function, capital function f, and we define it by, and here left hand side, right hand side, both of them have the s, y, g 10, so we should combine them. So it's s plus y plus g subtract exponential s, y, g. Okay, so again, if s, y, g satisfy this equation, then once you apply in the capital function f, you will get it's equal to 0. And now we consider its gradient capital F of s, y, g. Okay. So now we should consider its derivative. But here we have, okay, so we consider each 10. So consider, if we consider its derivative with respect to x, then view yg as constant. So first 10 is 1, second 10, third 10 is 0. But this 10 subtract exponential function is derivative. Outside function is exponential, so its derivative is self. But we should consider inside function is derivative. Multiplied by inside function is derivative. And now variable is x, so it becomes yg. And now variable becomes 1, then we have similar form. Here is 0, 1, 0, and here is itself. Multiply by inside function is derivative. Variable y, so it's xg. And the last term, syg, variable xg, so it's 0, 0, 1. 0, 0, 1. Subtract itself. Multiply by inside function is derivative. Variable is g, so we still have a constant as y. Constant as y. And we plug in the point 0, 1, 0. 0, 1, 0. So it becomes here, once we plug in the value 0, 1, 0, you will see here the value x is 0, y is 1, g equals 0. So here g equals 0. This term is 0. So we don't need to calculate this term because it's 0. And here we have g, so it's also 0. And now we have the x value equals 0. So it's also equals 0 this term. This term. So it's easy to see it's 1, 1, 1. It's 1, 1, 1. Its gradient is 1, 1, 1. Its gradient is 1, 1, 1. Okay, so now we could write down the tangent line and the normal line. And the normal line. And again, just the vector is the coefficient 1 times 1 times this term plus 1 times this term equals 0. Equals 0. And the 1, 1, 1, this vector is in denominator 1, 1, 1 in its symmetry form, symmetry equation. And this one, here we put the point x 0, 1, 0. I mean x subtract 0, y subtract y0, g subtract g0. And the s0, y0, g0 is 0, 1, 0. So it's s subtract 0, y subtract 1, g subtract 0. This one. And then here is s subtract 0, y subtract 1, g subtract 0. This one. And we are done. It's the normal line and tangent line. Sorry, tangent plane. Sorry, it's not line, it's tangent plane. Sorry, I should correct it. Tangent plane, sorry. Tangent plane. Okay, I think that's all the material in chapter 11.6. 11.6. So chapter 11.6 is a little complicated, yeah. And yeah. Okay, that's all.